Over the course of the last 4 videos, we learned about digital computer images and saw how to convert color images to grayscale. And then we went ahead and implemented an algorithm to generate straight lines between points on a white background that could potentially represent nails and threads that we would need to generate string portraits. So in this video, let us see how we can use what we have learned thus far to model and tune a system that could generate string portraits. To do that, let us first define and understand the problem clearly. What exactly is that we have to do to make string portraits? In our version, we are making string portraits of grayscale images. Therefore, we have to convert color images to grayscale, and we have already seen how to do that. The next step is to set up nails on the canvas, and we have learned how to do that also. That leaves us with the last step, where we have to decide the set of nails amongst which we have to string the threads, which could potentially result in a realistic rendering of the input image. There are two ways we can go about this. In the first method, we take individual strings of thread, tying them between pairs of nails until we hit the string portrait that we wanted. To be clear, I want you to notice here that two individual pieces of strings are not connected to one another, or the choice of the previous string does not affect the current one. So every single piece here is independent and unconnected for most part. The second method, however, works with a single piece of a long string. We tie one end of the string to a random nail, and from there we work our way through different nails until we end up with a satisfactory result. So obviously, in this method, we end up with an ordered list starting at some random nail of our choice. When you compare this method to the previous one, not only is this way more elegant, but also way less work. And that is because 1. We do not have to spend time tying threads between nails each time. And 2. The first method requires you to select 2 nails each time you tie a thread, and the second method requires you to select just one. This drastically reduces the computation required to make these choices. Therefore, we are going to design the algorithm to follow the second method. Oh, and also one more thing. If you were to design a machine that could automate this, then too, the second method would be the clear choice because then the machine design would be much simpler. In the last video, we saw how to generate all possible strings for a given number of nails on the canvas. So, if we are given a picture whose string portrait has to be made, the question is, how many of those strings do we have to use? Which are those? And how do we select them? How can we come up with a mathematical model that could do all these? To answer that question, we have to look at the structure of a digital computer image, which is just a matrix of pixels, and each of which consists of just one number. In reality, these pixels are made of 3 numbers, but since we are working with grayscale images, we just have to worry about one number, which goes into all 3 color channels. For our purpose, a digital image is just a matrix, and each cell in this matrix is just one number between 0 and 255. That's it. No complexity there. Now, on one hand, we are given an input image. Last time we wrote a function that could generate individual images of strings, and we could use that program to generate images of all possible strings. So on the other hand, we have hundreds of thousands of images of individual strings of threads. We would have to select a couple hundred or thousand amongst these and add them together to make the string portrait. That's it. That's the basis of our model. We just do plain arithmetic addition. Nothing more, nothing less. Let's imagine we have an input image that is 3 into 3 pixels big and also 4 different lines of the same image size. How could we combine these lines together in a way that the resulting image is gonna be equal to the input? Let's see. First, let us replace these colors with their numerical values and we get a simple matrix equation. Next, we have to equate corresponding cells on both sides. So for example, 130 is equal to A1 times 200 plus A2 times 255 plus A3 times 255 plus A4 times 255. If you do this for all 9 elements, you get 9 different equations using which you have to solve for the 4 unknowns, A1, A2, A3 and A4. Once you have a system of linear equations, the drill is to put them into a matrix equation and solve for the unknown vector by inverting the coefficient matrix. But to do that, the system must be solvable. That is, all equations must be linearly independent, and we must have at least as many equations as there are unknowns. If you did not understand a single word of what I just said, don't worry. I have links in the description which you could check out to learn about matrix equations and how and why they are used. This concept is very easy to understand and is fundamental to linear algebra. I suggest you pause the video and go check those out because why not? Unfortunately, we have two problems. One, our coefficient matrix is not square and therefore is not invertible. And two, the system of equations is not consistent and therefore it is not solvable. What does that mean? What is an inconsistent system of equations? Imagine you have a system of three equations in two unknowns: x plus y is equal to 10, 2x plus 3y is equal to 23, and x plus 7y is equal to 6. We could pick any two of these to find x and y. So taking these two and solving them simultaneously, we get x as 7 and y as 3. Okay, does this agree with the third equation? No. 7 plus 7 times 3 is 28 and not 6. This is what an inconsistent system is. There exists no value for unknowns in the equations that could satisfy all of them at the same time. I can give a mathematical proof for why our system is inconsistent, but I shall make a visual argument which is simple and intuitive. If you look at these two pixels and notice the corresponding pixels on our line image, you would notice that no matter how we combine these lines, those pixels would always remain white. Similarly, the opposite is true for this unshaded pixel. If you include this or this line in your combination, you would have shaded that pixel, which is not what we want. And if you don't include this line, then you would never shade this pixel, and so on and so forth. Therefore, no matter how you combine these lines, you would never achieve this image. Therefore, if you try to solve this system, you will find that there is no acceptable solution to these unknowns. You can go ahead and try, but it won't work. Okay, now what? I claimed a while ago that this is what we are gonna do to achieve string art, and apparently this does not work at all. Does it mean we have to abandon this approach? No, not at all. In engineering, we almost never look for perfect solutions, and trust me, this is an engineering problem. What we look for, though, is something that works well enough. So far in this series, we have come up with mathematical models for strings, for nails, and few other things, and all of these had one characteristic which is common, that the models we designed for them are almost set in stone. Like for example, we cannot model a thread as anything other than a straight line, a nail as anything other than a point, and so on. But I think we are at a point now where that ends and the room for experimentation starts growing wider. So what we are going to do from this point on will not be as dogmatic as before, and you may come up with improvements and whole new solutions than what you shall see here henceforth. Remember that. Coming back to our example, what would a solution look like if we could call it something that's good enough? The solution we have right now works well for the first two equations, but it is off the mark by 22 points for the third one. Is that the best we can do? Or can we come up with some other value for x and y that could make this a little better? If we take x equals 1 and y equals 7, then for the first equation, we would be off by 2 points. For the second one, we would be on point, and for the third one, we would be off by 44 points. That's obviously worse than before. What I want here is that the error between the solution and the system be as small as possible. Mathematically, if x1 and y1 is the best approximate solution, then I want the total error, which is the sum of errors of all equations, to be minimum. So let us generalize this problem and say we have a system of m linear equations in n unknowns. x1, x2, etc. are the unknowns in this system. a11, a12, a13, etc. are the coefficients of these unknowns as you see on screen. And b1, b2, etc. are the constants which the linear combination of these unknowns sum up to. Here's also the matrix form of the system, which makes our analysis much easier. Like before, we want to find a solution that has the minimum error with respect to this system. Let us denote the individual errors with E1, E2, E3, etc. And this time, instead of taking the total error to be the sum of absolute values of these errors, we shall take it as the sum of squares of these errors. This is because square functions are smoother when compared to absolute value functions, and it makes the calculus straightforward. This has a nice little name, and it is called the least squares method. And as usual, we write the system of error equations using a single matrix equation. We shall now do some calculus on this equation to find x1, x2, etc. that could bring the system down to a state of minimum error. That is E. The total error would assume the minimum possible value in this state. The total error E is a function of unknowns x1, x2, etc. and therefore we take the partial derivative of the total error with respect to each of these unknowns and set them to 0 to find the critical point of the total error function. It could be mathematically proven that this critical point is indeed the minimum, but it would suffice to say that the total error function is a strictly convex multivariate function and therefore the only critical point it has is the minimum. This is a quadratic function in a single variable, and you would be aware that this is a parabola on the Cartesian coordinate system. Similarly, a quadratic function of two variables is a paraboloid in three-dimensional space. As you can see, both of these are convex shaped and have just one global minimum as the critical point. The total error function is but a quadratic function of n variables, and even though we cannot visualize it, the same intuition could be used to convince ourselves that this function too has a single critical point, which is a global minimum. Coming back to our minimization problem and expanding each partial derivative, we get a set of equations with more partial derivatives in them. Each of these derivatives could be found by using the equation for the corresponding error, and they turn out to be just the coefficients of the unknowns. Putting all these together, we get a set of m equations, which could be written as a single matrix equation that you see. If you notice, the bigger matrix here is the transpose of our original coefficient matrix, and the smaller one is the error vector, which is just the difference between the linear combination of unknowns and the constant vector. Remember, the vector I am talking about here is just a fancy name given to a matrix with a single column. After some arithmetic and rearrangements, we get the x vector equal to a product of a couple matrices and the constant vector. I'll call this matrix product A plus, and this looks very similar to the earlier equation for which I argued the inverse for the coefficient matrix did not exist. This matrix A plus is called a pseudo-inverse of matrix A, and it solves the problem of error minimization which we defined earlier. This applies to both consistent and non-consistent system of equations. In the case of a non-consistent system, this gives a solution which puts the error between the solution and the system at a minimum. And in the case of a consistent system, it gives the inverse of the coefficient matrix, which by definition gives a solution with zero error. Let's use this pseudo-inverse technique to find A1, A2, A3 and A4 in our earlier problem to see if we can make something out of this. We already have this system in the matrix form as we saw earlier. So let's go ahead and find the pseudo-inverse of A and multiply that with vector B to get the values in vector A, which is our matrix of unknowns. I am not going to walk you through each step of the pseudo-inverse calculating procedure because there are a lot of tools online to learn how to do that, and also other tools and programming libraries which can calculate inverses very easily. Using these, I have already calculated this, and the vector A turns out to be what you see on screen. But there are huge problems here. Notice that A1, A2, etc. are decimals and two of them are also negative. Does this make sense? Remember, physically we can either choose to add a thread or choose not to add a thread. We have an intrinsic requirement for these coefficients to be whole numbers. Therefore, decimal numbers and negative numbers are unacceptable solutions for A1, A2, A3 and A4. Sorry to say, but this method is not suitable for our purpose because of these reasons, and therefore we have to find some other technique which optimizes for these coefficients subject to the following constraints. 1. These coefficients must be whole numbers, and 2. The result must give us an ordered list of nails between which we can string threads. So in the next video, we will see how to do that.